Okay, as we know, there is no decision procedure for validity in first-order logic. So the most common method that we use for establishing validity is formal proof. So we're next going to consider a Hilbert system for first-order logic. And this will be almost the last topic that will relate to any of the deliverables of the course. We're going to look at the Hilbert system, H, and we're going to take a good look at the deduction rule for first-order logic, because there's a slight complication in the way the deduction rule works in the case of first-order logic. It doesn't carry over directly from propositional logic. And once we've covered this Hilbert system and the new version of the deduction rule, as I say, that'll be more or less it for the deliverable portions of the course. There are some other topics that I'll talk about, but we won't enter into great detail concerning them. So let's set out the Hilbert system. First of all, the axioms. Again, this is called a Hilbert system because it consists of a number of axioms, and in the case of first-order logic, only two inference rules. The axioms are as follows. Of course, first-order logic essentially subsumes propositional logic. So our Hilbert system for first-order logic is going to subsume our Hilbert system for propositional logic. So the first three axioms will be of exactly the same form as for propositional logic. The first then is A implies B implies A is an axiom. And the second is A implies B implies C implies A implies B implies A implies C, as before. And then finally, axiom 3 is not B implies not A implies A implies B. 1/2, if you like, of the contrapositive rule. Okay. So those axioms are as our three axioms were for propositional logic, and we're going to use modus ponens again as an inference rule. So that means that every theorem that we proved for propositional logic has a direct counterpart in first-order logic. So all of the propositional reasoning that we did with our earlier Hilbert system carries over directly to first-order logic. But then we have a couple of additional axiom schemas that relate directly to quantification. So the first is for all x, A of x implies A of t. And there's a condition that applies to this axiom, which we will write out in a moment. You can't just substitute any term t for the free occurrences of x in A. Similarly, there's a condition attached to this last axiom schema, axiom 5. This says that for all x, A implies B implies A implies for all x B. So here we're assuming that x does not occur free in A. Specifically, in the first three axioms, A, B, and C are any formulas of first-order logic. I'll just say any formulas. And then in axiom 4, we say that T must be a term that is free for x in A. What do we mean by that? T, first of all, T is a term, so again that means in our present context that T is either a constant symbol or a variable symbol. But I'll write out a more general definition of what it means for T to be free for X in A. So this actually occurred at an earlier point in the notes when we were defining free and bound occurrences of variables. So let's say let's suppose that T contains a variable y. Then there must be no free occurrences of X in A. No free occurrences of X in A. That lie within the scope of a quantifier involving y. Okay. So for example, let's say that A is, for all y, pxy. And let's suppose that the term T that we propose to substitute for free occurrences of X is y itself. Then this T is not free for X in y. The idea intuitively is that when you make the substitution of T for free occurrences of X, in A, I should have said. The idea is that when you make the substitution of T for free occurrences of X in A, you shouldn't create any new bound occurrences of Y. However, in this case, if you substitute Y for X, then the corresponding occurrence of Y for X is going to be bound by that quantifier, whereas this X was a free variable. So the intuitive idea is that T is free for X in A if substitution of T for the free occurrences of X in A does not bind any variables in T. So that was the problem with this example. And if we substitute y for x in this formula, then that y is going to fall within the scope of this for all y quantifier, and it's going to be bound. So for that reason, we say that y is not free for x in this formula A. So again, in axiom 4, where in this case we have the formula for all x A, and the consequent is the formula that you get by substituting for all free occurrences of x in A the term t. Now, finally, in axiom 5, for axiom 5 there's also a restriction. In axiom 5 we were assuming that x does not occur free in A. So that completes the description of our axiom schemas for first-order logic. And I think you can easily convince yourself that with those restrictions that we've mentioned, these axioms are all valid. Now, what are the inference rules? As I said before, we'll still have modus ponens as an inference rule, but we'll also have another that relates to quantification. So modus ponens again states that if you've deduced A implies B and A, then from those you can deduce B. So because we still have modus ponens and we have axiom schemas of the same form as our axiom schemas for propositional logic, for anything we can prove in our Hilbert system for propositional logic, we can prove the corresponding theorem for first-order logic. The other inference rule that we add for the case of first-order logic is what's called generalization, gen. And this states that if, say, we have deduced A, then from that we can deduce for all x A. Hence the term generalization. So this idea, of course, relates to our definition of semantics. We said that a formula A is true in a given interpretation under our definition if and only if its universal closure is true in that interpretation. But that is the case if and only if for all x A is true in that interpretation. So in other words, under our definition of semantics, if A is valid, then so is for all x A. So this generalization inference rule makes sense. It should be noted that both our axiom 4 and this generalization rule differ from those used in the text. I think that this proof system is far preferable to the one given in the text, which has some weird properties. So let's take a quick look at one simple derived rule. We know that the theorems of propositional logic carry over. Many of the derived rules as well, because many of the derived rules that we had in propositional logic followed immediately from theorems of propositional logic. So those derived rules will carry over as well. As I said, the deduction rule doesn't carry over directly. But before we go on to the deduction rule, let's take a look at the relatively simple case of the specialization rule. Sorry, the relatively simple case, of the derived rule we call specialization. So by axiom 4, we have for all x, a of x implies a of x itself. Now x is free for itself in A, because in substituting x for any free occurrences of x in A, we just preserve the same free occurrences of x in A. Any new occurrences of x will simply be free occurrences. They're not going to fall within the scope of a quantifier for all x or there exists x. So if the term t referred to in axiom schema 4 is x itself, that's not a problem. X is free for itself in A. So we have this as a theorem of our deductive system. And as a consequence, we have the following derived rule by virtue of having modus ponens as an inference rule. And we'll call it specialization. And it's simply that from for all x, a of x, if we can deduce that, then we can deduce a of x itself. So we can get rid of the universal quantifier. So that's a relatively straightforward derived rule. And you can easily check, according to our definition of formal semantics, that if for all x, a of x is valid, then so is a of x. So that's interesting. That's a derived rule that we didn't have before, obviously, because it relates specifically to quantification. We did earlier have a deduction rule for propositional logic, but as I've said, that does not carry over directly to first-order logic. And our modified version of the deduction rule is going to be the topic of our next video. So I'll see you in that video.